In this video, we're going to work on finding the derivatives of different logarithmic functions. In a previous video, we did lots of examples of finding the derivative of the natural log function, or ln function. In this video, we're going to focus more on logarithms of different bases. So not base e, but of different bases. Like in this example, we have log base 4. And to help us calculate these derivatives, we're going to use the fact that the derivative of log base b of x is equal to 1 over x times the ln of b. So just as a quick example, if we wanted to find the derivative with respect to x of log base 5 of x, that would be 1 over x times the ln of 5. And that's the derivative. Now let's take a look at the derivative we're asked to find here. We're given f of x equals 1 over log base 4 of x. Now, because this is a quotient, we could approach this using the quotient rule. However, that's not the approach that I would take. If you choose to take that approach, go for it. But in this example, I would argue that it's not necessary because our numerator is a constant. I would tackle this derivative by moving the entire denominator, log base 4 of x, up into the numerator. In the denominator, the exponent of log base 4 of x is 1. If we move that expression up into the numerator, that exponent of 1 becomes a negative 1. So now we have f of x equals log base 4 of x to the negative 1 power. And now we can tackle this using the chain rule because we have a composition of functions. In this case, the inside function is log base 4 of x, and that function is being raised to the negative 1 power. So let's let u be log base 4 of x, our inside function. And that means that u prime is 1 over x times ln of 4. And if u is log base 4 of x, that means that y is u to the negative 1 power. And y prime is negative u raised to the negative 2. And the chain rule tells us that the derivative of f of x is equal to u prime times y prime. U prime is 1 over x times the ln of 4. And y prime is negative u raised to the negative 2 power. Simplifying that expression gives us negative u to the negative 2 over x times ln of 4. And if we move the u to the negative 2 from the numerator into the denominator, it makes the exponent positive. So that gives us negative 1 over u squared x times ln of 4. And now for u, we substitute back in log base 4 of x. So in the denominator, u squared is equal to log base 4 of x squared, and that's multiplied by x times ln of 4. And that's our final simplified derivative. In this example, we need to find the derivative of y equals 7 times log base 3 of the quantity x cubed minus 1. Here again in this example, we have log base 3 of a function of x, not just an x. So again, we'll have to use the chain rule because this is a composite function. Just as always, u will be our inside function. In this case, u is equal to x cubed minus 1. And the derivative of u is 3x squared. And if u is x cubed minus 1, that means y, our outside function, is 7 times log base 3 of u. And the derivative of y is 7 times the derivative of log base 3 of u. So we have 7 times 1 over u times ln 3. And you know what? I just realized we have a lot of y's going on in this problem. Our original function is a y, not an f of x. And we defined our outside function to be y and the derivative of that to be y prime. So this is getting a little bit confusing. So what I'm going to do, instead of naming our outside function y, I'm going to name it w. So that'll give us w and w prime. And the derivative of our original function y will be u prime times w prime. U prime is 3x squared, and we multiply that by w prime, which is 7 over u times ln 3. Carrying out the multiplication gives us 21x squared over u times ln 3. And now everywhere we see u, we substitute back in x cubed minus 1. And that gives us our final derivative of 21x squared over ln 3 times the difference x cubed minus 1.